Okay, let's start. Hello. Yeah. Uh, this is lecture number 28. Do you have any questions? Sure, I will do that. Let me just finish this thing and I will put the assignment. I want to first put the assignment solutions and then do it. Oh, yeah, I will do that. So, in yesterday's lecture, we just briefly talked about the power supply rejection in PLLs. Okay, so and we told that the most important block with respect to the noise in case of PLLs is VCO. Means other blocks are also important, but VCO is very important block. So let me just draw which noise are we considering here to show, and then you have a VCO. So what we are considering is the noise at all these supplies, even at the means all the digital blocks also they have some noise on the supply. So we were considering the so we were considering noise at all these supply voltages in the PL. Okay, and then we started looking at a power supply noise rejection, which I defined as PSNR is the short form for that in dB, and this was defined as 20 log base 10 of delta T by T divided by delta VDD. Okay, so let me just make this bracket base 10. This is the power supply noise rejection in PLL. Okay, now looking at the VCO, we had so we were considered. So one case is when we look for PSNR, if you consider all the differential cells, then the noise is limited, depending on whether the noise appears as a common mode or differential. Means the noise appears as a common mode in case of differential cells. So let me just show you that. Why are we only considering the ring VCOs specifically? So if this cell is treated as a delay cell in VCO, voltage control ring oscillator, then the output VOP, VON and VOP means provide if whatever noise exists on this supply, that noise exists as a common mode to the output. So provided the resistance behave linear, you will not have any noise at the output. So we have seen that we have different kinds of resistance implementation, and some will have a better PSRR as compared to the others. Okay, whereas in the case of ring oscillator, where this is all directly connected to supply, this ground, and this one is VDD. So any noise here directly appears at the output with whatever the gain it has. Okay, so for this, I think yesterday I also told that if I consider, so this is V control. If I consider F out is equals to KVCO times V control, and now V control itself acts as a VDD, means VDD itself acts as a V control, In that case, any noise, any frequency at any given time t is KVCO times whatever VDD supply you have for this particular VCO plus whatever overriding noise you have. I am noting it at small VDD. That will be the change in the frequency you will see. So then you will see the phase, how the phase output changes at any time t, which is nothing but 2 pi integral of f out dt. And you can find the PSNR for this particular ring VCO. Okay, so that was just a recap what we talked about yesterday, and now we will look at a supply regulation of the VCO. Yeah. Right. Yeah. No, if it is moving by a common means, if VOP and VON both are shifting by the same amount, right, then the differential swing doesn't change. Which one? Uh, yeah. Why do you say so? Well, let's see. So let me, if that's the doubt. So let's look at this. I have in a differential cell. So the question is, what I'm saying is in a differential cell, I am having VOP and VON as differential signals at a given common mode, right? Now, what am I doing with the changing the common mode? So if I change the common mode because of the change in the supply, now I'm riding on this, right? So what you are having as, so if you look at a signal swing, there is still differential with respect to the, means these swings are not going to change. Now, if in case you say that I am changing, let me say, okay, let me pick up another color. If you are thinking that this thing is changing with respect to common, no, that is not the case here. Means that will not cause any trouble as such. So think that this cell is connected to the next cell, right? Now next cell will also see, everything is seeing a shift in the common mode, right? So what you will not see any like change in the swing as change in the swing itself. The problem will be if one resistance changes differently with respect to the other, right? Then you convert into a differential mode. Common mode noise gets converted to differential mode, and that actually happens because you want to control this resistor with some MOSFET resistance or some different kinds of cells, right? So in case, so we have seen different kinds of Miniatis cell, we have checked, we have seen that, right? So if you do not do, means if the resistance is linear, then I versus V curve in any branch is linear. But what we have seen, because you use a MOS resistance, you have a VDS effect. So you have something like this. So provided at any place, let's say this is the common mode voltage, VCM. So in one case, when the swing is lower, you are at a different node, and the swing is higher, you are at a different node. And the incremental, that means you can see an incremental picture of the impedance dV by di, that is a different. So you will see a different output swing. Whereas in case of Miniatis cell, you have something, depending on where your limit is, you have some similar curve like this, right? A symmetric curve, symmetric impedance at the 2 points across the VCM. So if you look at a small signal impedance, let's say here, certain delta away, and a small signal impedance here, which is certain delta away, you will find the same impedance change with respect to the supply noise. So that will not create any problem. But Means differential cell has like inherently they have immunity to the common mode noise, but that completely depends on the impedance which you are using here, and then you have to come up with a different kind of like a much more linearized load to have that common mode rejection from the noise, whereas nothing of that sort exists in case of your ring oscillator. Whatever noise appears as a supply, that will come at the output. Okay, so does that clear? Yeah. And you are saying, yeah, I apply it in place of a differential cell, I apply it to pseudo differential. Means if everything is linear, then differential to pseudo differential will not create any change. So let me. Uh, no, the duty. So I think there's slightly some confusion which you are having right now. So let me do it this way. I have this resistor. I'm going with the pseudo differential, right? This is VDD. And let's say this current is, we are keeping the current. So what we are doing here is we are V in, this is V out, right? In all these differential cells, whatever I is flowing, let me call this as I out, that has a linear relationship with respect to GM, right? Now, if you are having a pseudo differential cell, let it be. So what did you do in, so let me call this as VIP and this is VIN, right? So this will, I will change it to VON and VOP, right? Now, you consider, let's say VIP and VIN, they are fixed at a given common mode voltage, and whatever the VDD is, your VOP and VON both will be shifted by that common mode voltage, right? So there is no problem with respect to that. You do not see any problem unless these resistors changes due to the supply noise in the difference VOP minus VON. Now, if this cell is used, so okay, this whole cell is becomes one single cell, and now this is cascaded, right? So the common mode of each of the cell is getting shifted, but every cell is getting shifted, right? So if every cell gets shifted, it might be consuming more current, less current, depending on how the common mode is getting shifted. And in case, so that is in a zero differential case, right? But in case if I have a fixed current source, right? What will happen? Nothing. If VIP and VIN shift by the same common mode voltage, your this potential will get shifted. Okay. So that buffer is zero differential is this without this current source, right? So there will not will you see any problem there with the, so okay, let me ask this question. Are you considering that, sorry, here I have the VCO, right? And now I am connecting to the buffer, which is a pseudo differential, right? So okay, now are you considering any noise on this, which is that okay? So what's the, okay, so now what you are saying is that the common mode here is getting shifted because of the noise, the wheel supply noise. Is that the question? Yeah, it will get shifted. So the output of the VCO, so that's what we have seen here, right? The output of the VCO will get shifted with the common mode. Okay. Now, if you are saying I'm applying this output of the VCO to any buffers, okay, then surely you will see the duty cycle problem. But we do not do that because we always have an AC coupling cap here. You cannot rely on the common mode of the VCO where the supply is regulated and the buffer which are running on the full supply. You always have a common mode shifting there. Okay. So any other. Okay. So now we will talk about the supply regulation in ring oscillators specifically. I would go with this right now. Okay. So what we have is so this is a ring oscillator. I will just draw a simple one all the time, but just to clear it, that you have this inverter chain connected. The number of inverters depend how you design it. This is VDD of the ring oscillator, and you have a ground. And we are considering all the noise at the supply right now, not at the ground. Okay, so let me, because I'm going to use this simple block. So this is VDD or VCO, and this is ground. So this is the model I'm going to use. Okay. Now the thing is, I want to control the supply of this regulator, so that I reduce the noise. So I have VCO, and right now I call this supply as, let's say, VS, and there is something in between the real supply VDD. I have to put something here. Okay. From here to here, there is this is the part of the regulation which we need to study, right? Okay. So there are. So we have seen that one particular regulation which we saw the other day was a source follower. Sorry, a voltage source follower, where I have this as a VCO, and so this voltage is coming from your loop filter. This is VDD. You have ground, and this is ground. This is VS. This is the regulation which we saw the other day, and here you see all whatever means the regulation, supply regulation for this VCO depends on the supply regulation on the of the amplifier. But the problem with this kind of amplifier was that all the current which is basically going into the oscillator has to come from the amplifier. Okay, so it just puts a more current requirement on the amplifier, and which turns out that it is like maybe a 5 times more current what the current which you consume in the oscillator. So we went ahead and said, in place of having all the current coming from the amplifier, I will have a pass transistor, VDD, and V control. So now all the current for the VCO is coming from the pass transistor itself. So this relaxes the current requirement on the amplifier. Okay, but this has two kind of paths for the supply noise. One path is coming from the supply. Means we cannot say that the amplifier is a clean supply. One noise is coming from the amplifier, and the other noise is directly coming from the pass transistor. Okay. So now the question is that, okay, we know that there can be different kinds of amplifier, there can be different kinds of current source. So let's break this into two parts and say this is the amplifier part, okay, and this part is an output part, output stage. So let me just output stage. Why we break into two parts? Because it very much depends what kind of amplifier are you going to use and the output stage. So let's look one by one. So output stage, okay. So this can be two kinds. One is a PMOS output, and other is NMOS output. So PMOS output and NMOS output. Okay, so for PMOS output, we have, so any noise is modeled as small VDD on this, then whatever fixed supply voltage you have for PMOS, and I'm modeling the equivalent resistance of the VCO as load RL. This is the output VCO node, which is Vs, or let me start calling it as V out. Okay, and this is the gate node, right? So in the regulation, there can be two conditions where the gate of the PMOS transistor is tightly coupled to VDD, or it is coupled to ground. Means the VDD doesn't affect the gate of the PMOS transistor. So you can see there PMOS has three terminals. Right now I'm not considering the bulb. So the drain terminal is the output noise. The noise is directly coming on the source terminal. It can happen that the gate terminal also sees the same noise, or it doesn't see any noise. So we consider both the cases. So one case is where it is grounded. So in this case, your V out of S with respect to VDD of S is equals to, if the G, let me just call this as M1. So GM1 times RDS1 in parallel with RL. Okay. Since you can work this out, the expression, you have this gain. So if there is any supply noise, then let me just write this as a small. So if there is any supply noise, that comes with the gain of the PMOS transistor. Is there anything wrong in the expression? If it is, let me know about it. Okay. Then the other case is where the PMOS gate input is also seeing the same noise as the source input. So VDD, RL, and this is V out. Okay. So in this case, what will be V out of S over VDD of S? Pardon? No, we are considering RDS. So if you consider RDS, you will have this as RL by RL plus RDS. VGS is 0. So means the small signal incremental will have this, right? This term goes 0, but the other term is there, right? So the thing is, we cannot actually neglect RDS in all these transistors, because the reason will be, I will just tell you in a while. So okay, so you see the two cases. If we tightly couple the gate with VDD, we have a gain factor there. If we do not couple the if we do not couple the gate with VDD, we have a gain factor there. If we couple with VDD, we have a resistive divider there. Okay, and why RDS is important? Because so ideally, what you want RDS to be infinite, right? Ideally, RDS should be tending to infinity, but you cannot have that, because then you need to have a larger overdrive, which will lead to you lower, for a given supply, it will lead to a lower V out. So that is going to limit your frequency of oscillation. Okay, out, lower F out, frequency of oscillation. Your range also gets limited. So there is always a limited, means only always a finite dropout which you would like to have, not more than that. Okay. So This is for the PMOS output. Then for the NMOS output, we will do the same thing where I have, sorry, ground VDD RL. So what will be the V out with respect for this node? So anything? Pardon? Huh? It will be RDS. No, we are considering the GM. You see, right? Here in this particular case, you have, so let's not make any, you have GM1 minus V out. This is RDS 1, and I'm applying a noise here, VDD, and this is RL. So this one is V out, right? So you have minus GM V out plus VDD minus V out by RDS1 is equals to V out by RL, right? So what you have is, if anything is wrong, let me know. V out into 1 by RDS1 plus 1 by RL plus GM equals to VDD over RDS1, right? So V out by VDD means it will be something, if you consider GM is very large, it will be something GM by RDS. Okay. So you see, when you're using an NMOS as an output stage, where the gate is not tightly coupled with the supply, at that time you see a gain which is inversely proportional to the gain of this bypass transistor. Okay. Then the other case remains is where I have the supply here and VDD RL, and this is V out. So in addition to the expression what we have here, we have minus, sorry, we have GM times VDD minus V out. Okay, means this is actually acting as a source follower. So I can, means without going to the expression, I can easily say that V out over VDD of S can be close to 1. So now you see that depending on how the gate is control of this output stage, you will have the regulation to the you have the supply noise regulation to the output control voltage of the oscillator. Okay. Now whether you will have the gate tightly coupled or not, that actually depends on the amplifier stage. So let's see that too. So you can have two ways, which is NMOS input stage of amplifier where okay. So this is, so let's just call this as VA and okay, and this is VDD. So now you consider the noise at the out on the supply and find what is VA over VDD. Is let's assume that you are not having any mismatch in the devices and everything. What will be VA over VDD? Pardon? So you can consider that you do not have any means current source is ideal. So that means what you have is means I think this should not be a so this becomes a for a small signal incremental this becomes ground. So you have right and all the noise is considered here. Okay, I'm asking for this as a VA. Huh? VA by VDD. It should be 0 or what it should be. There is no current no current can flow here, right? VDD will come, right? So this factor should be 1. In this amplifier stage, you see a complete coupling of the gate voltage with respect to the. You forget all the capacitors which are coming here, but this is the case. Okay. Similarly, for PMOS input stage, you have okay. So for the PMOS input stage, I am again looking for the amplifier output VA of S. So what do we have for PMOS thing? VA of sorry, just a minute. For this, we have VA of S by VDD of S. What should be in this case? Huh? 0. That is basically VA by VDD is infinite. Means sorry, this is 0. So now you see the combination of the amplifier with input stage. Amplifier plus output, sorry, not input stage. Your output stage, you're considering for regulation. So you have NMOS input amplifier plus PMOS output stage, then NMOS input amplifier plus NMOS output stage. We look at all the 4 combinations and see which one can work better. PMOS okay. So now can you tell me which combination are the better combinations in both these amplifiers and the first one and last one. So first one is NMOS input stage where your output is means VA is tightly coupled with VDD, and you are having a PMOS output stage where your PMOS output stage you are having a resistive divider, right? So that is the first one. So okay, whereas when you have an NMOS output stage, you have seen that sorry, NMOS input amplifier and NMOS output. Pardon? For PMOS common source. Right, right. No, so we are saying, so NMOS input amplifier tightly couples the VDD noise to the output of the amplifier, right? So that will, if we are using a PMOS output stage, that becomes a second case here, not the first one. So then it becomes a resistive divider. So you have a gain less than 1, right? Whereas if you do it with the case as the first one, which is, no, I didn't get it. Amplifier is giving the supply noise. So you see, amplifier is giving the supply noise, noise on the supply of the amplifier to the output of the amplifier. And if you use an input amplifier, then it says that the supply noise on the amplifier is directly coming at the output of the amplifier, right? So if we use this case, this one, then your VDD, the gate is getting coupled to VDD with the amplifier, okay, and the noise will already existing on the source side of the PMOS. So then it becomes a resistive divider, right? So either you consider, if you are using an input amplifier, then your gate is tightly getting coupled to VDD. So you consider either this case or you consider this case, an input, right? And an input, the gain is 1. So surely your PMOS case is better with an input amplifier. Similarly, you consider for a PMOS where you are not actually getting coupled, you are not coupling it, right? So in that case, you consider the following two cases. One is this one where you are having an amplification factor of GM into RDS RL, and the second one is 1 over GM RDS 1. Okay, so the better options to consider are these two. When you are considering the supply noise regulation, means this is for these two kinds of amplifiers and the output stages. I'm not talking of any complicated other method. So don't take it always as a general one where you may be using a folded cascode or some amplifier and say, because an input pair is always better, so I will use the an input pair. Okay. The only problem while using an NMOS output stage is that you need a certain, or you can say you need to have a larger overdrive. You cannot have a low dropout voltage across the NMOS transistor. That's the problem. So let's just see both of them. So let's say we can have whichever amplifier we want. The supply voltage is limited in both the cases, something as 1 volt. Okay. So we are looking at this as V out. Okay. So assume that you have only the control voltages which are limited by supply voltage between 0 and 1. Let me not just go beyond 0 and 1 volt. Okay. In which case you will have a V out which is higher. And without doing means the only thing is you need to keep this current source in saturation. Right? So in the case of PMOS, you can have a higher V out. Means the maximum you can go on the NMOS gate is 1 volt. In order to make it work, you have to come down a threshold voltage down. And then V overdrive down. So where your means you use both NMOS and PMOS regulation. PMOS regulation mostly for oscillators where you want a higher output voltage to run at a higher frequency. If the higher frequency is not the requirement, if you can go to a lower voltage, then you will go and use an NMOS output stage. It's not used here, but it is used in some kind of, just for your information, when we want to use a voltage mode transmitter where the supply is very much low, there you can use a NMOS output. V overdrive, VDD minus V overdrive. So let's say at max, V out max for PMOS case is VDD minus V overdrive. Now I'm asking the question that the gate volt I am not means even this can go to a the means you need to only keep the MOSFET in saturation, right? NMOS in saturation. NMOS in saturation, the VDS should be V overdrive, right? So if you are just looking at VDS, your V out is VDD minus V overdrive, both the cases. But in order to have V out equals to VDD minus V overdrive in NMOS case, what should be the gate voltage? VDD minus V over, so let me just say VG minus VDD minus V overdrive VGS minus VT should be equals to V overdrive, right? Which is VG is equals to VDD plus, tell me if I'm wrong any place, minus 2V overdrive. Sorry. Is it? I'm finding the gate voltage. This is VG, this one is VS to keep it in saturation. Okay, let's do that way. VDS, so the condition is should be greater than VGS minus VT, right? Where your VD has to be greater. No, here we are trying to find the condition on VD, right? VG, and your VD is how much? VDD minus V overdrive. This is what we are trying to have it. No, VS is cancelling in both the cases, right? So I'm not taking that. This is the only thing which I am saying. So the easier way you can work out in this means forget the equations right now. So you need a certain VD sat is equals to the V overdrive, right? Now VD sat, you can, if you maintain your VDS is equals to VD sat, right? So in that case, if VDD is 1 volt, your V out can be 1 minus V overdrive, and I'm just finding the minimum gate voltage for that. So what should be minimum gate voltage for that? So that is what I said here, that I have VG, okay, this is VGS minus VT should be equals to V overdrive. Should be greater than VT. So that's what I am trying to say. That if you limit your supply voltage control to all the supply voltages, you cannot reach that higher swing. So not always you can use this NMOS regulation. It all depends on the frequency which you want. Okay. So now let's see the PLL with this regulation. So let me use an input pair with PMOS. Okay. V control, and this one is VDD. This is VDD ground. Okay. Okay. And we consider noise on both of these. So what we have just seen that, okay, this will all the DC gains kind of thing, but we need to see with the real some kind of capacitance in the system. So let change this amplifier with the NMOS input where we have effectively some GM block. Let me just call that as GMA. Okay, and the output resistance of that GMA is ROA. I'm fine writing that as an effective gain and so let me just write it as RA amplifier. Then you have a capacitor at the output, which is CA. Okay, so let me just write this node as Vx and this is V out. Vx. Then I have PMOS plus RDS of the PMOS MP and effective RL, and then there is a capacitor at the output C out, and all this is connected here, and this is the place where we have noise. We are injecting, and this node is connected to your V out. Okay. And this one is your V control. Fine. And this value is GM of the PMOS. So let me write it as GMP times Vx minus VDD. This is. Okay. So this part is just all of this part is just an amplifier part. I'm just modeling it as an effective GM with RO and CA. Okay. The interesting thing is if you do the analysis and if you do not consider the noise on this resistance RO of the op amp, you will find a different noise and you will see some different characteristics. So while doing the analysis, you cannot neglect that the noise is directly coming to the output resistance also. Got that point, right? Okay. So V out means now I will write it directly. You can work this out later that V out by VDD of S is equals to S times VDD. We'll define all these parameters. S VDD divided by 1 plus S by omega out into 1 plus loop gain of regulator. Okay, now SVDD is equals to RL by RL plus RDS P. Omega out is 1 divided by RDS P parallel RL times C out. Okay, and loop gain of our regulator is gain of the amplifier AA and the gain of this output stage divided by 1 plus S by omega out and 1 plus S by omega A. Okay, and in this A of the amplifier is GM amplifier times R of the amplifier. A of the output stage is GM of the pass transistors times the R output stage in parallel with RDSP in parallel with RL, and omega A is 1 over RA times CC. Okay, so this is for the transfer function with this. So the other way I can write this also, because you see that loop gain of the ring PLL is having two poles and divide. So this can also be written as SVDD into 1 plus S pi omega A into 1 plus S by omega A times 1 plus S by omega O plus A naught and A amplifier. The other one is a more simplified form which I showed. Okay. Now, the important part which you see here is that depending on means from supply noise to the output, you can see a zero depending on which pole dominates or which pole location it dominates, right? So if I plot this one, so at DC you have, what's the value at DC? You have SVDD divided by 1 plus loop gain of at DC. Then in case your omega amplifier is much lesser than omega out, you will have a zero coming in, and okay, this slightly there are something kind of this, where your this location is omega A, somewhere you will have omega O. So this is with respect to omega, and this is V out by VDD. Okay, now that. Okay. And the regulator bandwidth will be somewhere here. So this is the transfer function which you will see from V out, sorry, VDD to V out, which is here V out is what? That is the control voltage of the oscillator. Okay, and from control voltage of the oscillator to the phi out, the phase output. So let me just, is there any question with this? This is just a calculation, sheer calculation. So we know that phi of out by, in this case, means, let me just rename so that it becomes, this is also the V control of the oscillator. Okay, the node is also the V control of the oscillator. So this by V control of the oscillator, what will be this? KVCO over S into 1 by 1 plus loop gain of PLL, right? In case when you are considering the whole PLL loop, you know, there's frequency translation and one integration, right? So you know that 1 by 1 plus loop gain is a high pass transfer function, and 1 over S is KVCO over S, which should occur near the PLL bandwidth. So the transfer function of, so let me just write it as phi out by V control is something like this, where this position, I mean, this is independent of the loop which we are considering. This position will be something as omega PLL. Okay. So this is phi out by V control, and you know VDD to V control. So you can multiply these two to get the phi out by VDD, which will be the just the product of these two. So depending on where your omega PLL and where your peaking appears in the noise transfer function from the supply to the output, you can have a peaking in the noise at the output due to the supply noise. So we will see this thing in more detail tomorrow. Let's stop here.